So what happens now with the motion of the magnetization when we apply such an RF field and it induces a flip angle? Let's look at the laboratory frame of reference. Then we have the Larmor equation, which says the derivative of the magnetization with time is equals to gamma times the magnetic field. And the magnetic field I have conveniently split into the B1, which is time dependent, and B0, which is constant. So now what happens is, actually in the motion is, as we apply the B1, it rotates with omega RF. As the B1 is in the transverse plane and it rotates, the B0 will start to, the magnetization will start to deviate from being along Z. The minute it starts to deviate from being along Z, it will start to precess. It will precess with a Larmor frequency, which is on the order of 100 megahertz. We have seen with the examples for the B1, this is on the order of kilohertz. So this will go 100,000 times around in circles for every rotation that it makes around the field B1. So what happens in the motion is that we have the B1 field here that rotates. And now what I will describe here is the motion of the transverse magnetization and the longitudinal magnetization as we turn on this rotating reference frame. So we have the B1 applied at Larmor frequency in the transverse plane for a time tau, and this will create a nutation of the magnetization in a spiral motion as it tips away from the Z-axis. So let's look at this in the animation. The B1 makes the magnetization rotate, so the transverse component increases, the longitudinal component decreases until we're done, and we have done a 90-degree excitation. Now remember, this is happening, the rotation is happening 100,000 times for each rotation that we flip the magnetization. So it's difficult to visualize, but we'll illustrate this effect of the B1 in the experiment that we have done with a simulation of the magnetic resonance effect with this experiment with the yellow magnet that is rotating. And we'll look at this experiment now.
So in this experiment we have the same setup as in the experiment I showed last week, but we have an additional magnet here which produces a magnetic field that's perpendicular to the main magnetic field, which is this way, and this magnet in here produces a magnetic field this way. And so, as we have seen with the equations in the course, having this magnetic field rotate at the frequency, Larmor frequency, will induce the change in the orientation of the magnetization vector, and that's what we should be seeing here. So I will bring it into rotation, and then as I turn it around, you can see how it goes down and then tips at the end. So this is the same rotation motion. If I take this is my B1 field here, magnetic field this way. If I take this out and just give it a spin here for the ball without this B1 field, then it will precess in the external magnetic field like we have seen last week.
Okay, so we have seen, we can visualize that if things are going slow. Now in reality, things move around at the Larmor frequency in the 100 megahertz range and rotate into the transverse plane in the kilohertz range. So putting ourselves into the rotating frame of reference, where we no longer consider the motion due to the B0, so this term is cancelled by the omega RF over gamma, then we have, in the rotating reference frame, we have this equation of motion to consider. So in this rotating reference frame, which rotates exactly at the Larmor frequency, we have a B1 that is stationary. We'll look now here at the Z magnetization, and we'll look at the transverse magnetization. And the B1 field now will rotate the magnetization towards the XY plane. The way this works is the X component increases, the Z component decreases. This is a simple, in this reference frame, is a simple rotation, because in this reference frame, the B1 is stationary. The amplitude of B1 determines how fast we get towards the transverse plane, that is how fast it is rotated, and we can calculate the flip angle if we know the gyromagnetic ratio, the B1, and the duration of the application of this B1, which is also called the RF pulse. So that's the flip angle given. After the application of this RF field, the Z magnetization is equals to m0 times cosine alpha. We have rotated by angle alpha, and the transverse magnetization increases with sine alpha, so it's given by m0 sine alpha. This is when we start out with the equilibrium magnetization. To give us an idea in MRI, what is the gamma B1? So we'll look here at frequency. So gamma B1 over 2 pi is typically from anywhere from 0.1 to 1 kilohertz. This means that the duration of these RF pulses, where the RF is turned on, is typically on the order of milliseconds. For all practical purposes, this is all that we need to know here. So now we have talked about nuclear magnetic resonance. So we have had the term nuclear, we had the nucleus involved, we have a magnetic field, so we have the magnetic in there, but we haven't really talked about what resonance means. Let's look at the excitation with the B1 field. And the question we're asking here is, how does applying such an RF pulse, so an RF field B1 that we apply for a certain time tau, how much can we get excitation? That is, up to what range, how close do we need to be to the Larmor frequency that we can generate an excitation that is a rotation into the transverse plane? So now if we are in our radio frequency field or rotating frame frequency omega RF, which we will choose always such that the B1 becomes stationary. This is the simplest way to describe it, and here omega, the frequency, angular frequency of the rotating frame, becomes the angular frequency of the reference of the radio frequency. So omega RF. So if we are now away from the Larmor frequency, so we have a delta omega that's non-zero. And in this case, our magnetization will experience a effective field that is given by gamma B effective, which is given by gamma B1 squared plus delta omega squared, and that's the square root. How does this come about? Well, we have seen if we are in a rotating reference frame that does not exactly match the Larmor condition, then we have a residual Z magnetic field along Z, and that is here given by delta omega. We are by definition in a rotating reference frame where gamma B1 is stationary. That is, so gamma B1 is stationary, and our magnetic field along Z is given by delta omega, which is given by gamma B0 minus omega RF. And so we have a Z component of the magnetization, it's stationary. We have a transverse component of the magnetization in our reference frame, that's stationary as well. So this is the vector addition. This gives us an effective magnetic field, B effective, that's tilted by the angle theta. So what does it mean now? We have the Larmor equation, and Larmor equation is always true. So we have now the rotation axis is dictated by the direction of B effective. So it is tilted by an angle theta compared to the transverse plane. If we were exactly on the Larmor frequency, delta omega would be 0, theta would be 0, and we have the case that we have discussed last week and just before. So here is now what I'm going to plot is to illustrate this. We have the z-axis on the vertical. We have the equilibrium magnetization that we start out with. And this little sphere here indicates the tip of the magnetization vector. So that's the magnetization tip. It's easier to describe this with animation. Now we'll apply in our rotating reference frame a B1 that is constant, but we are not exactly at the Larmor frequency, so we have a delta omega over gamma, that's the delta B that is left. So we have also the Z component. So this corresponds to this, and this corresponds to this, so we get a B effective that's in this direction. Now, the Larmor equation says our magnetization, which is initially here, it will, only its component perpendicular to be effective will change. The one that's parallel will not change, so we will get a circular motion around B effective, and here is our circular motion. So our magnetization vector here will rotate on a circular motion around B effective. Now here the particular choice of delta B is such that B1 is equals to the delta omega over gamma, so we have a 45-degree angle. And in this case, we are still able to get the magnetization from being along Z to being in the transverse plane. But remember, when we had the B1 only here, we were on resonance, this term is 0, so the B effective is along B1, then we can easily rotate it also into the minus Z orientation, the magnetization. Here, with this particular condition, we are no longer able to do that. Now let's take the same situation. We'll start out with the magnetization, shall be the same. Here's the magnetization vector tip. I'll apply the same B1. This shall be the same B1 as here. But now, let's say we are applying this B1 field at a further away from the Larmor condition. So we're further away from the precession frequency of the magnetization in the absence of a B1 field. So now our B effective is given again by B1 and the Z component. That's the mismatch between the frequency at which B1 rotates and the Larmor frequency. And now we have the motion again by the Larmor equation given by precession around B effective, and now it precedes on this conical motion, on this circular motion around B effective. Notice here that the magnetization is now no longer able to reach the transverse plane, so we're no longer able to excite the magnetization fully. I'll take a third example. We'll start out again with the same magnetization. Here's the vector tip, the tip of the magnetization vector. We'll use the same gamma B1, so the same B1, and now we are even further away from the Larmor condition with the frequency of our B1. So we are rotating, the B1 is now applied at a frequency that's far away from the Larmor frequency. Our rotating frame is far away from the gamma B0. In this case, we have a residual Z component, delta B, which is delta omega over gamma. So that's B0 minus the omega RF over gamma. And the B1 has stayed constant. So our B effective is now tilted more towards the vertical axis. The motion is again by the Larmor equation given by this circular motion perpendicular to B effective. Now you can imagine, as you go further and further away from the Larmor condition, the Z component of the effective field will increase. The frequency by which the magnetization precesses progressively increases, but the flip angle, maximum flip angle, which is this point here that we can obtain, decreases and decreases, and at some point we won't be able to produce any motion of the magnetization that is discernible, and nothing happens. So clearly, if the frequency of the RF field is too far away from the Larmor condition, we're no longer able to produce excitation and have the magnetization in the transverse plane. So this condition here, where we have considerable alignment of the effective field with Z, where essentially nothing interesting happens, is called off resonance. The B1 is much smaller than the delta B, and essentially the effective field is more or less parallel to Z. Whereas if we have on resonance, then on resonance it suffices to say that the gamma B1, so this vector, is much larger than the delta omega. That's this component here. And in this case, essentially the effective field is parallel to B1, and we have the situation of the stationary B1 field on resonance. So this is the situation of on resonance. We're close to the Larmor frequency, and close here means that gamma B1 has to be big compared to the mismatch between the radio frequency pulse frequency and the Larmor frequency. This is a reason why one in MRI applies radio frequency pulses for short duration of periods. One wants to have a sufficiently large gamma B1, and as an idea here, the RF field, the B1 field, is typically applied to for periods of around 1 milliseconds. As a rule of thumb, the RF field with an amplitude of B1 can excite a range of frequencies on the order of plus minus gamma B1. Here we can see here it is gamma B1. The delta omega is gamma B1 here. So, and here we still can excite. So in this case, that's the plus and minus, because we can do this also on the other side. Now there's a quantum mechanical equivalent. We remind ourselves we're talking quantum mechanics here. And this basically means we have, as we change the orientation of the magnetization, we also change the population of the energy levels. And the transition probability is highest if the photons, if we speak of photons here, the energy of the photons matches the energy of the energy, the difference of the energy levels in our nucleus. That's how we can induce transitions in the population of the energy levels. And this is illustrated here with people jumping on the bridge. If you do this with the correct frequency, then you get the maximum amplitude classically. That is what we've seen with resonance when we discuss in classical mechanics the harmonic oscillator. And on the right, you'll see the picture of the Tacoma Bay Bridge, famous example of illustrating resonance that's used in in a classroom context.